Assalamu alaikum everyone, welcome to the course of real-time embedded system. Today we will start chapter number 9 and the name of chapter number 9 is control system, and this is our lecture number 29. So this is our last week, and in this chapter we are going to talk about the introduction of control systems, open loop and closed loop control system, journal control system and PID control system. Along with it I will talk about software coding of PID controller, and finally we will end this chapter on PID tuning. So let's start with the control system. So in this slide we will talk about the control system of an automobile. So control physical system output. So the purpose of a control system is to control the output of a physical system. So here we can see that we have a velocity at the end of the physical system, that is our plant, which is automobile. So by setting physical system input, so we have to set this reference input, that is R of t, such that we can achieve some desired value at V of t. So for this purpose tracking, we do tracking. For example, we can do cruise control tracking, we can do thermostat control tracking, we can do disk drive control tracking, we can do aircraft altitude control. So all these are tracking. In cruise control we set a reference speed, in thermostat control we set a reference temperature, so we want our actual temperature to reach at the reference temperature, so this is called tracking. Similarly, for the case of disk drive control and aircraft altitude control. Now the problem that we face here is disturbance. As you can see here, we always arrange our controller like the way you can see here. We have a plant here. Plant is our system, and then we are providing this system with the input, that is u of t, which is actually the actuator throttle. So for example, if you're driving the car, what is in your control? The race or the throttle is in your control. So we can increase or decrease the throttle in order to increase or decrease the speed. So this external disturbance is acting upon the plant. You can see that we have road degrade. So if road is not good, we have more external disturbances. If road is okay, then we can like have minimum disturbance. So this is our control. So a function is applied on the input R of t to generate u of t, which is the throttle. U of t is the throttle which is applied at the plant input. So we have the reference input R of t, which is desired speed. What is our goal? Design f. So our function is to design f such that v approaches r. So this v should approach this r. And how we can do that? We have to design this f. Here's the control car model. V of t plus 1, that is the next state, next velocity or speed, is equal to 0.7 vt plus 0.5 ut minus wt. So this w of t is the disturbance, this 0.5 into u of t is the input, u of t is the throttle input, and 0.7 vt. So this whole thing makes up the car model, and this is the control law. So what we are doing, we're actually multiplying this control law. So here you can see u of t is equal to p into r of t. So we have to find out the some value of p such that we can control this v of t. So this r of t is our input, p is some proportional, that is like simple as in the case of PID. So this is just proportional, some fixed value, that is just like a multiplier. So our system model will become same v of t plus 1, 0.7 v of t plus, now we have to replace u of t with this p into rt. So 0.5 p rt, and we have ignored this disturbance because this is not a part of the car model, it's just like the external disturbance. We can also include it here, so it will become minus wt. So why do we have difficulty in order to model and control this? Because we can have disturbance due to wind, due to road, due to tire, due to brake, due to opening and closing of the door, or we can have human interference, which can be feel good or feel right. So for example, like if the car is going too fast, we're not feeling good. If it's going too slow, we're like having problem too. So like these are the major issues which result in difficulty in the control of car speed. So all these are external factors: disturbances, wind, road, tire, brake. Okay, so it can be tire pressure, brake condition, and all these factors includes to the difficulty in the designing the control system. So let's move on to next slide. So in this slide you can witness that the system output is on the y-axis, and on x-axis we have time, and this is our reference signal, that is the solid line. So now you can have any quantity, like system output can be speed, temperature, velocity, it can be acceleration, it can be voltage, it can be anything on the y-axis. So we have to generate our reference signal, and this is actually the system output, the dotted one. So our purpose is to design such a controller that this dotted or dashed line follow the reference input. So here we can see that our system output is like undershoot, or is staying under the reference input, whereas here in the next one you can see that we have an overshoot. So our purpose is to design such a controller that this dashed line follow the solid line. So this is called tracking. So in this slide we will talk about the open loop control system. Control system minimally consists of several parts, as you can see in this figure. So you have the controller, you have the plant, you have the reference input, actuator, disturbances. So the plant, also known as the process, so this plant is also known as the process, is the physical system to be controlled. So this is the system which we want to control. So in this case we are following the example of automobile. So in this case our plant is automobile. The output is the particular physical system aspect that we are interested in controlling. So we are interested in controlling this output. The speed of the automobile is an example of an output. So this speed is the example of output. So we have to control this. The reference input is a desired value. So this is our desired value that we want to see for the output. So we want this value to reach here. The desired speed set by automobile driver is an example of reference input. The actuator is the device that we use to control the input to the plant. So this actuator, we use this device to control the input to the plant. A stepper motor controlling a car throttle position is an example of an actuator. So in this case we are using an actuator which is basically controlling the throttle of position of the car. Finally, we have controller is the system that we use to compute the input to the plant. So we use this controller to compute the input to the plant such that we achieve the desired output from the plant. So we design this controller such that we achieve desired output from the plant, which is actually this one. And finally we have another parameter, that is disturbance. So disturbance is an additional undesirable input to the plant imposed by the environment that may cause the plant output to differ from what would have been expected. So what happens, this disturbance can actually change the model. So what we are expecting from the model can be disturbed by this disturbance. For example, wind and road grid are example of disturbances that can alter the speed of the automobile. Okay, so let's move on to next slide. So we have already discussed the output, we have already discussed the reference, and disturbance. So disturbances are basically, let me reiterate, that uncontrollable input to the plant imposed by environment. Wind, bumping the disk drive, door opening. So these are all disturbances. So in this slide we will talk about some other characteristics of open loop control system. A control system with these components, as you can see in this below diagram, is referred to as open loop because there is no feedback from output to input. So this is open loop or feed forward. So everything is moving from input to output. So this is actually the feed forward control. The controller reads the reference input. This is reference input, and this controller reads the reference input. As you can see that R of t is a function of this controller. The controller reads the reference input and then computes a setting for the actuator. So the controller basically computes the setting for the actuator. The actuator modifies the input to the plant. So actuator basically changes the position of the throttle by using some stepper motor, which along with any disturbance results sometime later in the change in the plant outputs. So this input basically changes the speed of the plant sometimes, and we are including the disturbance in it. In an open loop system, the controller does not measure how well the plant output matches. So we do not know that how well the plant output matches the desired reference speed. However, the open loop control is best suited to situation where the plant output responds very periodically to the input. So if we have a system that respond to the inputs and there is no like chaotic behavior or random behavior, we can use simply the open loop system. And we usually use the open loop system when we have an accurate model and disturbance effect is minimal. Okay, so best used for predictable system. If we have a system that is best model and disturbance is minimum, and for that purposes we use open loop. We know that if we are going to give it 50 rpm per second or 50 rpm per hour, so how it will react to the desired input value. So let's move on to next. So in this slide we will talk about the closed loop control system. Previously we have talked about the open loop control system, and we have seen that we prefer open loop control system when we have the plant which is accurately modeled and when the output of the model is predictable. So for simplicity we use feed forward and open loop control system. But in some cases many control system poses some additional part. As you can see here, we are measuring the output here and then we are using a speed sensor to find out the actual speed of the automobile. So we have a sensor measure the plant output. Then we have an error detector. This portion is error detector. It detects the error between the reference input and the actual speed. So this is E of t. A control system with these part is known as closed loop. So this is known as closed loop because our loop starts from here and it goes back from output to input again. We can call this feedback or closed loop system. A closed loop system monitors the error between the plant output and the reference input. The controller adjusts the plant input. So what happens on the basis of this error? The controller adjusts the plant input in response to this error. The goal is actually to minimize the tracking error given the physical constraint on the system. So our goal is to minimize this error. Okay, so once this error is minimized, our reference will be equal to actual, or our actual will be equal to reference. So in this slide we will talk about the steps of designing open loop control system. We are primarily interested in closed loop designing in this chapter. However, we will begin by providing simple example of open loop automobile cruise control system as shown in below figure. So these are the steps of designing an open loop control system. Number one, we are going to develop the model of the plant. So when developing the model of the plant, you must need to know how your model behave to the inputs, what are its input, what are its outputs. So first of all, develop the model of the plant. Second, develop a controller. So we will develop a controller. In third phase, we will analyze the controller. We will analyze the controller on the basis of input. So we will give input to the controller, and then this controller will be connected to the plant, and we will analyze the output. Finally, we will consider some disturbance, that is due to wind, due to some uh, disturbance road, and finally we will determine the performance, like how much overshoot, how much undershoot, how much settling time. So these are the steps involved in designing of a closed open loop system. So the example that we are going to follow here is open loop cruise control system. So just get familiar with this block diagram. We have reference input R of t, which is desired speed. Then we have an actuator after the controller, followed by the plant, which is our automobile. So what we have to do, we have to set some reference input R of t, which is our desired speed, and the plant should move at that desired speed, or the automobile should move at that desired speed. This is our car model, as already explained. This is our control law. Control law is simply some proportional multiplying with the input. So once you replace this u of t is usually the control law or the input to the plant. So if you place u of t here, we will get this system model. So this is the model of whole system. So let's move on to next slide. So in this slide, we will talk about modeling the plant. In many cases, controller design, our first task is to develop a model of how the plant behaves. A model describes how the plant output reacts to a function of the plant inputs and current states. For our cruise control, the model should describe how the plant reacts to the throttle position and the current speed of the car. As we will see later, we do not always have a model of the plant, and instead could design a controller through somewhat ad hoc experimenting. So one thing that we need to understand, that we do not have the model of the plant always, but how we can design the model by giving some input data and finding out the output. On the basis of input output pair, we can model the plant. We could see how a practical controller works and iteratively modify the controller input until the desired tracking is achieved. However, for many plants, like a car, such experimenting is dangerous. So using a model for experimenting is preferable. So not every time we can use the input data to give it to the plant and then find out the output, because for real-time system, doing experiment is very dangerous. So what we do, we have to have a model. So can make it easier to design if we have the model, may be useful for driving the controller. So first of all, we need to have the model of the plant. If we do not have the model of the plant, we can do experiments to find out the how it reacts to the input. But if we have model, we can make it design of the controller easier and may be useful for driving the controller. So the example that we're going to consider here is throttle that goes from 0 to 45 degree. Okay, so throttle is basically the input signal. Okay, so we control the velocity speed of the car by changing the throttle, that is your pedal. Okay, so it can go from 0 to 45. On flat surfaces at 50 miles per hour, on the open the throttle to 40 degree. So if we have flat surface, we can achieve a speed of 50 miles per hour, and we have to open the throttle to 40 degree, which is well in our limit. Wait one time unit. So we have to wait for some time, measure the speed, let's say 55. So we are measuring the speed and it is for 55 miles per hour. Now, then this finally the equation comes in. This is our system equation. V of t plus 1, that is the speed, next speed is equal to 0.5 into V of t, which is our current speed, which is 50 miles per hour, plus 0.5 into U of t, which is our control input. So let's say that our next speed is 55 and our current speed is 50, plus 0.5 into 40. So how we can compute this speed? If we are currently going at the speed of 50 and our throttle is 40 degree, so what will be our speed after this setting? Our speed should be 55. So if you solve this, 0.7 into 50 plus 0.5 into 40, you will get 55. If the equation holds for all scenarios, then we have a model of the plant. So if this condition holds for all the inputs, okay, then our model is validated. So this is how you can validate your model. Okay, so let's move on to next slide. So once we have the model, the second step that we are going to do is to design the controller. So initially in this example, we are assuming that our plant is very simple and we are going to use a simple linear function to control it. So here you can see that our plant is a function of r of t. Okay, so u of t is equal to f r of t. So we are just going to replace this function with simple linear function, that is p, and it is just proportional, and r of t is the desired speed. So linear proportional controller, so this is our, you can see here, this is our system model. So v of t plus 1, there is our next speed, is equal to 0.7 into current speed plus 0.5 into u of t, which is our control input. So u of t is equal to p into r of t, which we have replaced here. Now for steady state condition, we have to find out the, actually our goal is to find this u of t. How we can find out this u of t? We assume that in steady state condition, u of t and u of t plus 1, these two will be equal. So once these two get equal, we can find out the value of u of t in terms of r. So if we replace v of t plus 1 and v of t is equal to, both are equal to vss. Okay, so we have this equation, vss is equal to 0.7 into vss plus 0.5 p into r of t. So we can see that at steady state we want this thing. At steady state we want that our speed should be equal to r of t. Okay, so this speed should be equal to this r of t. Okay, so just replace r of t here. R of t is equal to 0.7 into r of t plus 0.5 p into r of t. So for this value, for p is equal to 0.5, we can do this. Okay, so if you put here p is equal to 0.6, we will have this equation satisfied, that vss is equal to r of t. So for 0.6, p is equal to 0.6, we can find our value. So we have found out the value of p. So u of t is equal to 0.6 r of t. So how we have found out this value 0.6? First we assume that our system is in steady state. So once our system is in steady state, next and previous is equal, both are same. It means that previous speed and next speed is same. So once our system is in steady state, we want that our steady state speed should be equal to our reference input. So we are going to find out the value of that P for which VSS is equal to R of T. So we have finally found out the value of point. So our control law becomes this 0.6 into R of T. So let's move on to next slide. So in this slide we will analyze our design controller. So here you can see that our initial speed is 20 miles per hour and our desired speed is 50 miles per hour. This is the equation of the system, that Vt plus 1 is equal to 0.7 into V of t plus 0.5 P. So this is our P, R of t. So just substituting the values, that 0.5 into V of t plus 0.5 into zero point 0.6 will be 0 0.3, and the value of R of t, that is our desired, is 50. So it will solve 2.7 into V of t plus 15. So the throttle position is, we know that throttle position is equal to, what is the throttle position? I've just told you. So it is U of t is equal to P R of t. So here P is 0.6 into 50, which is equal to 30. So our throttle position will be 30 degree. Okay. So throttle position will be 30 degrees. So here you can see here that at time 0, our velocity is 20. At time 1, so if you put 0.7 into 20 plus 15, you will get 26. So again, next time your current will be 29, so 0.7 into 29 plus 15, it will be 35. So this is how your velocity is increasing, and finally you will reach to 49. And our desired speed was 50. So with the help of this controller, our actual speed is basically approaching to 50. So it means that our controller is working fine. So let's move on to next slide. So in this slide we are considering the disturbance. Disturbance is of -5 miles per hour and 5 miles per hour. So in our previous model, once we are subtracting -5, so this will become 10, and when we are adding it to our model, it will become 20. So our model was, if you go into the previous slide and you see, our model was V of t plus 1.5 into V of t plus 15. So we are subtracting 5 from 15 and then we are adding, so we will get these two. So this is our previous speed output without any disturbance, and this is when we have disturbance of +5. Okay, so at the disturbance of +5 we will get this speed, and at the disturbance of -5 we'll get this speed. So this is how our output can vary in the presence of disturbance. So at time 0 all the speeds are same. So you can simply use 24 and you can put 24 here at V of t and then plus 10, and you will get this 26.80 for the next